a little bit more with our partial fractions. And that is just, you know, what we do with something. So I don't really care. On this, I'm not really going to worry about what the numerator is, so I just have some numerator divided by. And now, suppose I have a linear term, so x plus a, or x minus a, and then another linear term, but in this case, I'm going to raise it to a power like 3. And then times, and suppose we have a quadratic. And now the quadratic we could also raise to a power, but I'm not going to in this case. So I have an irreducible quadratic, and just to make life easy, I'm going to assume that c is positive and write it this way. I could have a middle term in there, a x term, but again, this is just to kind of point out what we do with this and what we do with that. In this case, what we end up doing, so our theorem says, well, this is going to be equal to, and I used lowercase letters there, so you know I'll use uppercase letters for the top. It'll be sum a over x plus a, just like we had before, plus, now we have to account for all possibilities of this x plus b. So we could have an x plus b, or we could have an x plus b squared, or we could have an x plus b cubed. That's a terrible 3, there we go. And so I'm going to call this b0 for, or well, we'll go with b1 since that's the first power, b2, b3. You don't have to use subscripts or anything like that, but I just thought I'd keep it with the b's. But notice, these are all still constants. So down here is a linear term, and I have a constant. Here, I actually do have a quadratic, but it's a very special quadratic. It's a perfect square. Notice that's still just a linear term, or sorry, that's still just a constant. That is also still a constant. So I had to account for all of the possibilities in the denominator, because certainly I could have had something like 2 over x plus b plus 3 over x plus b squared, and then something over x plus b cubed, you know, 7 or something over x plus b cubed. And when I add all those together and get the common denominator, that common denominator is x plus b cubed. So, you know, that absolutely could happen. And then for the quadratic terms, that's where if I have this x squared plus c, I would have a c1x plus c0. So here, notice we have to introduce that possibility of an x over that x squared plus c. So if I have a quadratic term down here in the denominator that's irreducible, then I need a constant times x plus another constant. And that's how I set it up. So you can see that, you know, all of a sudden now I have 1, 2, 3, 4, 5, 6 unknowns. So, you know, what looked like, it didn't look great down here with these 3 different terms. Well, yeah, it gets kind of nasty because now I have 6 unknowns. So these partial fraction problems can escalate out of hand very quickly, but that's the idea. And if this x squared plus c happened to be squared, well, I would have one term that could look like this on the end here, and then I would just do another term similar to what I did here. I would have the x squared plus c quantity squared, but again, the top would just be something that looked like that. anything new on top. Different constants, of course, so like maybe a C2 and a C3 or something. But they would just keep going. So you always will either have these constants over linear terms and their powers, or you'll have a linear term over an irreducible quadratic in its powers. So that's the idea with partial fractions. Once you get that decomposition there, you set it up the same way. You have to go through getting a common denominator and looking at numerators and matching up like terms if you do it the formal way, or pick